Okay, hello everyone. My name is Mateusz Pusz. I'm a C++ trainer and a chief software architect at Epam Systems. I work there mostly on the projects from the finance domain with high performance and low latency requirements. Today we'll talk about stud variant and how to use it in order to replace polymorphism, which is a problem in the projects I work on. First, why I care about it. As I said, I'm working on low latency domain. Latency basically is the time required to perform some action from the start to the end of it. And in low latency, basically we try to be faster than the competition. This is what we do. This is how basically this market gains money. In order to verify our software, in most cases we are not interested in the average performance of our product, but we are most interested in the worst case execution time of our project. That's why we operate on percentiles that you will see at the end of the talk. What I provide speaks about my domain. I mostly talk about things that not should be done on the low latency software, but things that you should avoid in order to not make mistakes. So these things are, for example, to not use tools that trade the usability for performance, like shared pointer, stud function, to not throw exceptions on the likely code path. Exceptions are fine, but as long as they don't appear on the hot path, they are not raised. Dynamic polymorphism is wrong, multiple inheritance, RTTI, dynamic memory allocations. Today, we'll scope mostly on those two subjects. So, how to do it? This is typical case of dynamic polymorphism. We have base class, we have a class X and class Y that inherits from the base class, and they implement the interface. Then we have, in most cases, to dynamically allocate the child class, and we refer to it from the base pointer interface like this. And the solution I wanted to provide here for you today, we will talk about the variant. In this case, we have two structures, X and Y. As you can see, they are not related to each other. They have similar or the same interface, and with variant you can put them to one object B and call visit on them. That code is shorter, it's faster, it has value semantics. As I said, it works on unrelated classes, and it's more flexible because you may have different signatures here a bit as long as they obey the rules of that visitor. We don't have penalty for this virtual dispatch here and for this allocation. And basically, that's all. This is the talk, this is the feature I wanted to share with you today. If you have any questions, then please, but I have also quite a few bonus slides if you want. There will be a lot of them, and we have only 24 minutes left, and we started late, so I hope to go as much of them as we can. Yeah, so bonus slides. For an example of the technique, we'll talk about the finite state machines. Probably more than half of you implemented at least one of those in your life, because this is what we do all over again. This is the example for today. We have three states: idle, connecting, connected. States are changed in the finite state machine and based on the inputs they received. Those inputs are called events. We have events like connect, connected, disconnect, and timeout here. You can see that timeout for the state, it depends on some predicate here that determines if you are still doing the reconnect or going back to idle. The change from one state to another is called a transition. And this is defined with a list of states, the initial state marked with this circle here, and conditions for each transition. So, case number one, single dynamic dispatch. We'll implement such a class diagram that has some base implementation for Finite State Machine, that stores a state that has onEvent function, virtual function. States will inherit from it, and we have enum as an event. So it can be implemented like this one. It has non-copyable virtual destructor and pure virtual function. Our Finite State Machine will store it as a unique pointer here, and we'll call dispatch here. That's why it's called single dispatch, because it does it only once. We have state, we call on event. On the event we received as an argument of the function. If we return something different than null pointer, we have a new state, so we have to switch the state in the machine. It's called dynamic because we have virtual functions here. Virtual in most cases nearly always means slow. And this is what we try to not use in our domain. So this is our Finite State Machine. And for the sake of the next slides, I will use such a using. Of course, I will not use it in the production, but it makes my slide easier to read. I have to implement all of the states. All of them has the onEvent function, and this is how it's implemented. For the first one, we implement moving to the connecting state. On the another one, we have two possible events to come. So we either move to the connected or idle state. And the last one will move to idle if event is disconnected. This is how we implement traditionally Finite State Machines. This is the slow part here. We have to make dynamic allocations. And for testing those transitions, we can use fold expressions from C++17 to pass number of events to our Finite State Machine, and we are done with testing of those. Single dynamic dispatch has such characteristics. It's open to new alternatives. You can always add a new state or a new event to this, and it will work fine. It's close to news operations. You have onEvent, and you cannot add any more without changing the whole inheritance, so whole the design of the polymorphic tree. It's multi-level. You can inherit from states that already are a child of the base. It's object-oriented. And yeah, that's all in this case. Another case to implement Finite State Machine is using so-called dynamic dispatch. So let's assume that we want our events to pass some data. For example, event connect to provide us information which address is being used for the connection. In such a case, we could do this, yes? But it turns out to be a really bad idea. So we are using double dispatch, also known as a visitor pattern, and it involves two objects and dispatch between them. So this is our event. Right now, event is not an enum anymore. It will be another polymorphic tree of classes. It will have pure virtual function dispatch that takes the state. Our Finite State Machine right now would not call onEvent onState. It will call this dispatch function. So this is the first dispatch in the double dispatch pattern. We have to implement those in every event. And as you can see, we then call onState onEvent. So we call the second dispatch, providing current object with current type, already being specific type, not the base type, to states. With that, our state has to have different interface. It has to be overloaded on all the events we have in our system. And all of them are virtual functions. By default, I assume that we are not changing the state for them. It's null pointer, so the Finite State Machine will stay in the same state for each of those events. And this is how we implement for example, state idle for one of the child classes. This is class diagram of this solution. So you can see that it's a pretty complex tree right now with a lot of dependencies. And it is fixed by the implementation details, in fact. We cannot change it easily. One thing that bothers me here is that if I will have like 100 events, I will have to rewrite that exact thing each time. So CRTP comes handy here. We provide as template parameter the child type of the event, and then we statically cast it to this child and call it an event on this. So thanks to that, we can type it like this, or even have all the implementation right now on the slides, and everything fits fine. Transitions. In this case, we don't use if or switches like in previous case. We have already dispatched everything fine. We know that in state idle we will be having event connect, and for all the other states we also have all the dispatch done for us. So now we only implement the behavior. So moving to the state connecting, state connected, idle or staying in the same state, and to idle. This is the slow part, yes? Once again, dynamic memory allocations. For testing of transitions, we use similar dispatch function, and this time it's important to notice that once again we have to allocate memory for events. In most cases, in most of the implementations. And once again, this is another slow part in our design. So, to summarize, dynamic dispatch is pretty similar to the single dispatch, with the difference that it's not open to new alternatives. As you remember right now, the state has virtual functions on every event you have. So in order to add a new event to the Finite State Machine, you would need to modify the base class in the interface in the library. So going to the fun stuff, yes, going to the variant, because this talk is about variant, not about the old approach. First we'll consider and talk about the introduction to variants. I try to do it on 3 slides in 3 minutes. So if you are not familiar with variant right now, that was introduced in C++17 is different from the Boost version we had earlier. It represents a type-safe union that in most of the cases holds the value, but it can be also in a special state called valueless by exception, which is basically a compromise, DZIP compromise, in order to not have dynamic allocations that were done in Boost. This is the conceptual simplified interface and implementation of it. So we can think that variant is something like a union of different types. This is not a valid C++, of course. And it also stores an index of the current active option in our variant class. Stud variant in C++ standard library is not allowed to allocate dynamic memory. There's a difference from the Boost one. It doesn't hold references, arrays, or void. Empty variants are informed, but you can use something called monostate to simulate the empty variants. It's permitted to hold the same value more than once, and when it's default initialized, it initializes the first option of the variant. This is how you do dispatch on variant. So you can either do it dynamically with the index member function, or in most cases, it's preferred to use visitor. Visitor is a simple functor with overloaded call operator for each of the types of the variant. Then you call studVisit and provide the visitor as the first argument and the list of variants that you would like to pass to this visitor. You can provide more than one here. So let's come back to our Finite State Machine. Right now we can define events as not related classes One of them will store the address, another one will be empty, and we put everything to a variant of events. We do the same with states. To implement our transitions, we will create a struct called transitions that will have overloaded call operators for all of the possible transitions we defined in our Finite State Machine. So we have a state idle with event connect, state connected with event connected, state connecting with event timeout, and state connected with event disconnect. So all of the transitions here. And we define what is being done in each of those. And what we are missing here? Default, yes. What will be the default action? For that, we'll take greedy template that just says for all other cases, we are staying in the same case. Notice that I'm returning here optional of state, another C++17 tool that makes it really nice here. So our Finite State Machine engine right now is a template class template that has 3 arguments. It has states that are passed as a first argument to the visitor, as a first variant to the visitor, to the visit function. It has events, and it has the transitions, which in fact is our visitor class. Now we can state the state diagrams like something like this. So we don't have any inheritance. We have some classes that are unrelated put into the variant, and the design uses them in our engine. To test the transitions, once again, we have similar fold expression, and we are back to passing objects by value. Like in the single dispatch, we don't have to allocate memory anymore. Another use case that may be interesting here is such an approach. We have, once again, Finite State Machine that have the same template arguments. No, it has different. It has derived right now. So when you see derived as a first argument, it means that CRTP will be probably here used. And we have visitor, similar to the previous one. So as a first operation in that function, we will do the static cast to a derived type. And with visit, we'll provide the lambda function for every state and every event that will return us the optional of state. And we'll pass it to onEvent member function of a child class of Finite State Machine. We are doing perfect forwarding here. Okay. So we can also lose the variant of events in this case. So right now we are only having variant of states. Events are passed as a template arguments, and we don't have to care about another variant in our design. Right now, with this design, we have the Finite State Machine defining all of the transitions. So in this case, let's say that our child class is a visitor with all of the transitions defined. And once again, we have all of the transitions defined explicitly and the default at the end. This is similar to the previous case. And this time, our class diagram shows that events are not related to each other. They are loosely coupled with all the design, and basically you could use and add any event to the design if needed for those. I have also one more case that we can use here. It will have the most complicated implementation, and basically I'm in favor of the previous one, not that one. But that's interesting because that makes it similar to the double dispatch, where all the logic is put into the states, not into the Finite State Machine itself. So in this case, we may have once again the dispatch function, and we have so-called overloaded, which is a new pattern that is coming in C++20. So beware, lambdas are coming. This is the first one that takes any state, and in case our state has an event for specific event provided by our template argument, it will pass the Finale check and will return optional state variant and do an event on this state. In order to handle all the defaults in this case, I have another lambda that is a worse overload because of the template argument parameter pack that calls the policy provided as a template parameter to the Finite State Machine. And again, providing transitions is really simple. Right now we are doing this in state. It looks really similar to the double dispatch approach, but we don't have any virtual dispatching or dynamic allocations. And this is our default. Yes, this is the policy we use for all of the cases. We can do null opt, we can throw an exception, we can do something else here. So why we are talking about this? We are talking about performance, yes? So I did some micro benchmark of this, but they provide some numbers, but you will find the real numbers in your project. You always have to measure, like Fedor said on the previous presentation. Micro benchmarks are synthetic. They have, in most cases, hot caches. They not represent the real life. I must say that when I use those techniques in my finance project, we really seen those changes visible on the large scale of the project. In all of the timings, we've seen improvement, not only some specific small part of it. So basically, it was visible from the project scope. So it's enough to care about it. For micro benchmarks, I use bigger Finite State Machine. So I implemented the TCP state diagram like this one in order to make sure that the branch predictors and caches will have a bit harder work here. And these are the results I got. So these are the single dispatch. You can see that on the x-axis we have percentile. It's not linear scale. And these are nanoseconds. For double dispatch, it's of course slower because we have a lot more dynamic allocations to virtual dispatches. For this approach, with variant, any of those that I presented, it's much faster and much more deterministic, even in the worst 99.9 percentile here. And this was the slowest one I measured. So for low latency stuff, for things that need high performance, for things that you must be sure about the worst execution time, I would recommend using such techniques. So to summarize, variant versus inheritance. In case of inheritance, we are open in case of single dispatch and closed in case of double dispatch to new alternatives. In case of variant, we cannot add new states to the variant easily, but we could add also events if needed. But basically it's Finite State Machine, so it will not have more states, so we are fine. It's close to new operations. In case of inheritance, we cannot easily add new operations. In case of variant, we can add more visitors doing different stuff. As you've seen in, for example, second case of variant, our states, our events were dumb class that didn't have anything or had some string view inside. They didn't have any operations. All operations were done externally to them, so you can always add more operations doing the same. Inheritance is multi-level. You can inherit whole hierarchy tree from the base class. In case of variant, you have single level of the, let's say, inheritance. One is object-oriented, another one is functional. One has pointer semantics, another one has value semantics, which is very important here, which makes all of this stuff easier to handle. In case of inheritance, we had one fixed design that was forced by the implementation details because we decided to use polymorphism. We couldn't much choose what you would like. As you've seen, I've shown you 3, but probably there are even more possible designs for doing this with variant. And you, as an architect, as a developer of the code, you are responsible to choose what you like, not what you have to do because the code has to be written like this. In case of inheritance, you are forced in most cases to use dynamic memory allocations. With variant, you don't have those. Strict interfaces in case of inheritance, so each state, each event has to have exactly the same signature as the base class. In case of variant, you have duck typing, you may have returning void or int. Your function may have, for example, default arguments, the default values provided for the arguments, so it will pass the duck typing signature check. I would say that inheritance is more complex, at least in the number of lines you have to write. In case of reasoning about the design, variant is simple, and yeah, we see the graph. Polymorphism is slow, variant is fast, and also in terms of 99.9 percentile, it means that most of the cases are at the same performance nearly. There are no spikes at the end that you will not expect in low latency software. So with that, that's all. I'm done, and do you have any questions? Oh. Hi.
So let's say that I present the opposite point. At the beginning, in his opening keynote, Björn told us that duck typing is bad. You're telling us that it's good. Personally, I would like to have both in my toolkit. But anyway, as you explained, the polymorphism-based version is open to new alternatives, but not to new operations. And you explained to us that the variant-based solution is closed to new alternatives, but open to new functions, right? So
yes,
I can see how it makes sense in the context of one application. And indeed, using a switch on a closed set of types can beat polymorphism. But I disagree with you on 2 points. If you want to write libraries, or even in the same company, share code between several applications, what you present is just not extensible. And my second objection is that the benchmarks you present, I find them unfair because to me it's a straw man. You're comparing performance of things which try to achieve different goals.
Yeah, I'm not saying that you should replace all of the polymorphism with variants because in many cases it will not be possible. Here you have options. You may choose inheritance, you may choose a variant, but you have benefits and problems related to each technique on this slide. It's up to you to decide which one you can choose or must choose in case the other one will not work for you at all.
Okay, I'm much more sympathetic to this because a little earlier we had a talk in this room which said that OOP is dead, and in the end the conclusion was these are just tools in our toolbox, and now
yes.
You're saying the same.
Yeah.
So in that we are on the same page.
Yeah, the session is over, so we have to finish this. But yeah, just to summarize, as I said, it's a technique that you can choose to use. Yes, it's not that you can replace every polymorphism in your design with that solution. It's up to you to decide.
Okay.
Thank you.